Okay, so I will discuss network now. Okay. So, there are different sorts of network, some are more efficient, less efficient. Okay, so, let us discuss the complexity. So, as I said, every node is sending the data to a switch. That is a typical design. Okay, presently, the switch is the one which is used for communication, but that is not the only way. I will just make a remark at the end. Okay. That there is another way which is not being used, but there is another way. So, this is a node. So, this is a schematic. Okay. So, this you can think of a PC, PC 1, PC 0, PC 1, PC 2, PC 3, and they are connected by this links. So, in practice there will be this PCs, and wire will come from here and go inside a switch. Okay. And within the switch there will be links. Okay. So, this guy so link is within a switch, that is safe to assume. Okay. And this is a connection. So, I am saying is a linear connection in this schematic diagram. Okay. 0 is connected only to 1, 0 is not connected to 2. So, this is a wire, this is another wire, and this is another wire, the 3 wires connecting. Okay. So, there are few terminologies. So, what is the diameter? Diameter is longest distance between any pair of nodes. Okay. So, between 0 and 1 there is a distance is only 1. Do not think of the wire length, okay. Just think of discrete number, which is, so one hop is, you can think of hop. So, how many hops do I need to get data from 0 to 1? One hop, right. But I want to go from 0 to 3, how many hops do I need? This is not a link, this dashed line is not a link, this is not a link. 3 hops, 0 to 1, then 1 will send it 2 and 2 to 3. So, the longest distance is 3, and that is the distance for this network. Then we have links. So, number of links or connections in the network, we have 3 wires, okay, 3 connections. Degree, the number of in and out links at each router. Okay. So, here there are 2 links, right. Here in 2 there are process 2 the 2 links, but 3 and 0 have 1 link. But if it is a long linear chain, then you can say, well, average is 2. We can ignore the endpoints which are only 1. So, that is in and out link at each router. And average distance. So, average distance between any 2 randomly selected nodes, you can find the average, okay, is between 1 and 3. Okay. So, I did not compute it, but you can compute that average. Then we have bisection bandwidth. This is another important concept. So, minimum number of links that needs to be broken for partitioning the network into 2 equal halves. So, right now if I break this link, then the 2 equal halves, right half and left half. So, you need to break only 1 link. Okay. If it is a complex network, then you will definitely need to break more than 1 link. And bandwidth. So, capacity of a network to transmit the maximum amount of data at a given time. Okay. So, how much data can it transmit? Maximum. Okay. So, this is like a peak rating, and speed is this is slightly different. So, this is maximum and speed is kind of average. Okay. There are technical differences between the two, but right now you can just think of bandwidth is maximum possible and speed is what you get in general. Okay. So, then let us look at some switches. We come across this switch. My picture was this taken from somewhere. Okay, I should have cited it. I think I have. Okay. So, this is all to all connection. So, how is all to all connection? And in one hop. Interestingly, this just in one hop I can reach anywhere to anywhere. So, let us imagine I want to go from 3 to 5. whether these are switches. Huh? Okay. So, right now I think everybody is off and I turn on this one, these two lines. So, data will flow like this and go like that. Okay. So, we have n squared switch and you just turn on one particular switch to facilitate appropriate data. Okay. This transmission is done by the 3 will send the data, it has some signal saying that I want to send to 5 and that will automatically enable, you do not have to do it, no person sits there and enables it, but these are all electronic. Okay. So, so this is all to all connection. The problem is if a large number of, well, you can think of this as a process and this is data or memory, okay, or it could be process and process. This set of process want to talk to this set of process, okay, but so it requires n squared, right? If n to n talking is requires n squared, and now the number of processes are already in 100,000 or million. So, million by million is impossible to connect. Okay. So, this is not practical, okay. It is very expensive, not practical for large number of nodes. In fact, for 100 itself it becomes a problem, there are too many wires. So, what do? I go for typically architecture like this. So, linear is not crossbar, no. Linear is, I mean, this guy is 0 cannot talk to 3 in one hop, we saw that. It requires 3 hops. This is a ring architecture where I connect 0 to 3 by one additional wire. So, what is the advantage of this wire? Right now it is all uniform. Well, of course, from 0 to 1 is 1 hop, 0 to 2 is 2 hop. Either you can take this side or even that side you can go this way, then that way. Okay. We added a wire, but this is more like a uniform structure, it is called ring, and well, at least the maximum distance we have covered, we have made it half, okay, right. So, ring is useful for simple one wire connection and it makes the maximum distance in half, right. Is not it n by 2 now? Suppose we have long chain and I want to go from here to here, okay, and if the ring is connected. So, I will not go from this side, but I will go from this side. So, that makes it n by 2. Now, this for 1D, we can also think of 2D. So, 2D we have square architecture or torus architecture. So, what is a torus architecture? So, torus, everybody has seen torus like donut or cycle tube. So, how do we construct a torus? So, just think of that this is our 2D grid. So, there are points. So, there is a point here, there is a point here, okay, and this side also there are points. So, to make a torus we just connect this point to this point first, okay. So, this is a cylinder. Now, I am identifying this unit to this unit. So, you should not put a point here as well as there. For periodic boundary condition, we start from left, the end point should not be allocated. This point should be same as this point. So, you do not have it at all. Okay. There are people make mistakes of that sort. In data we have right point is not to be included. Okay. So, here, so this is one, and then, so right now I have left and right are same, right, but I want to make these set of points equal to this set of points. So, what should I do? I should fold it, no. So, well, I can't fold it, this is not very flexible. So, you just turn it around, fold it. So, you get a tube like that, and so this is the torus. So, but torus you do not need to have a tube in your computer center, you do not want a tube. You just have to make one wire and attach it like that from right from the top to bottom and from left to right. Okay, that is a torus. Now, we can just work out various diameter, bandwidth, link and degree for this 4 architecture. For linear we already done it, well I showed it for 4, but for diameter will be p minus 1, bandwidth will be band cross section bandwidth, okay, where I cut it is 1, links is number length p minus 1 and degree is 2 except at the end points, but which will be ignored for a long chain. Okay. For ring is p by 2. So, these numbers I will not discuss it, you can just work them out. Okay. A degree for example, for square is 4, right. There are 4 links from each node, and for torus also is 4, the diameter has reduced, it was 2 times square root p minus 1, it is square root p. P is the number of nodes. Okay. So, here there are 9 of them. Now, cross sectional bandwidth. So, I need to cut them, right. For this 2D I can cut here, and that will divide in, well it is not equal half unfortunately, because I have 9 points. Had it been 16 it would be equal if I just cut right in the middle. Okay. So, how many nodes I am cutting? Right now I am cutting 3, for 16 I will cut 4. So, that is square root of p, square root of 16. Okay. So, that is square root of p. Okay. For torus you need to cut twice that. So, if you cut only once, the torus it will remain a cylinder, right, and then you need to cut once more to cylinder is there connected, but you again need to cut once more to make it fully connected, disconnected. Okay, let us move slightly faster. So, those are 2D architecture, but now 3D architecture is cube. Again I will not discuss these numbers, this is called hypercube. Okay. So, diameter is log p to base 2. Okay. For example, this guy wants to talk to this guy, it will do in 3 halves, here, here, here. Okay. So, square root of log 2 of 8 is 3. Okay. And so, I think these numbers I will not discuss them, it is pretty much straightforward, but I want to tell about hypercube. Okay. So, this is a cube, and how do I make a hypercube? 4 dimensional cube joining the vertex with another cube. So, that is a hypercube. In fact, the analogy is that we have, so basically this is also called torus, hypercube is also a torus. So, we just have to connect the endpoints. Okay. So, the endpoints are the vertex and you connect the vertex. So, this is T, this is called T3, well this is T3, this is not T3, this is a cube. Okay. So, torus is with a 3D cube connected made into a torus is T3. I want to make T4, then what will I do? So, I can take 2 3D torus T3 and connect them by wires. So, in a cube there are 3 connections at each vertex in a, so we just had to take a 2 T3 and add them. So, we can continue like that. Okay. So, this is how we construct, you just have to connect the endpoints. Okay. So, I think this bit complicated stuff, but this is how wiring is done, and this Japanese machine Fugaku, which was number 1 1 year back, has a T6 connection. Okay. So, the engineers who connect them will be go crazy, you have to connect all the wires. So, it was a 6. Now, there is another architecture called tree. So, please remember this is less than a crossbar, number of links are less, but it can handle more nodes. It is a tree, no, this one is a tree. So, we have 8 nodes and they are connected via a tree. So, I want to go from here to here, what will I do? So, I have to go up that way, that way, that way, this way, this way. So, it has many hops, but we can reach anywhere to anywhere via these connections. If I want to go from here 0 to 1, then I can take just one hop. And this is something called fat tree, which is a tree, but the number of the bandwidth of the wire is more when you go up, because these channels will have more data transmission. right. I want to talk from this to this, I have data go like that, from here to here again data flows like that. So, we want to have more bandwidth when you go up. So, this is why it is called fat tree. Okay. And fat tree diameter is log p to the base 2, okay, times 2. So, it is the depth of the tree multiplied by 2, because I go up and then go down. Okay. And that what is the depth of a tree? This is the depth of the tree, log p to the base 2. Okay. So, that is you can just work it out. The tree is you can go to the node in that many steps, log p to the base 2. Had it been linear, it would be p, but it is decreased. So, linear search and binary search. Binary search is faster because we adopt tree structure, and the bandwidth, bisectional bandwidth is 1. Okay, you can cut any this one, that is it gone. So, this is called dragonfly. There is another architecture called dragonfly. So, it is like a fractal structure. Okay. Nodes are here, and these nodes are connected to each other. This is also called star connection. Okay. Any to any. Okay. So, it is like a crossbar if in some sense, but connection is, you can see, is a star connection. Now, this two guys can talk via wires, this pink wires, but again I want to connect them via all to all. So, this all to all connection at different levels. To go from this node to this node, I can't do in one hop, but I can do in 2 hops. Okay. So, this is a fractal structure. You can, I hope you know fractal. So, it is an important thing, you can just read Wikipedia, but I think everybody should know what the fractal is. You can look at, by the way, here if I treat this is a single object, one unit, then the connections will be exactly same as what is there inside. It is all to all within this block, not within block, but if I make that as one unit, then again it is all to all. But then I can make similar units like this, 6 of, well, how many are there? 6 of them, okay, 6 of them, and again connect them. Okay, in a similar way, that will be level 3 structure, and that is a fractal structure. Okay. Like a tree has a fractal structure, the main branch, then there are branches, and within branch there are further branches. So, this is a fractal. Well, it has advantage that we can reach faster than a linear or even torus connection. So, things are organized in nature mostly as a fractal. So, this is a picture of a switch, okay, InfiniBand switch. It was manufactured by Mellanox, but now NVIDIA has bought this company. So, this is basically like a this dimension could be around 5 centimeter. Okay, and now, so these are the ports where the wires go in. Okay, and InfiniBand is one of the big brand for HPC. It facilitates very fast connection between nodes. Now, I saw the top 500 list now, and there are lot of supercomputers are using 100 Ethernet switch, which was not fast, but now people have come up with strategies to make it fast. So, 100 gigabits per second is a pretty fast speed, which we see that in InfiniBand offers slightly faster, but same order. So, Ethernet has become fast over time, and this one picture of Ethernet switch. Okay. So, this is the connector. You can, by the way, you can buy this connector and put in your PC if you want to connect to a gaming device or something. So, these are available to fast connection between 2 devices. So, I had shown a connector inside our Sanganak machine. So, this is a connector, in fact, which is cooled for whatever reason. Okay, I mean to make the things do get heated up. This is a table taken from Wikipedia. You can look at one number. So, unit is gigabits per second. Okay. If you have one link, this is for InfiniBand. So, this is called FDR switch. F is for 14, okay, that is some number which is FDR. It is one of the common switch. So, there are various category. SDR is single, DDR is double, QDR is quad. So, this FDR is 14. So, this is like 14 gigabits per second, which is pretty fast. And if you put more links, then of course, you can multiply that by 4, you get this number, okay, 4 links. Multiply by 12, we will get this link. Okay. So, more links, more transmission we can get through this switch. Now, these are SDR is also available, high data rate, okay, and that goes up to 50 gigabits. XDR is I think extreme, which is 250. Okay. So, these are some are not available, they are projected for future technology. Okay, you see here 23. So, this is available now, SDR and NDR they are available. So, yeah, you should keep this number in mind, but now just connect how fast was RAM. So, RAM link for ROM was 256 gigabytes, no, not yeah, I think 200 something, right, 256 I think gigabytes, it is 200 gigabytes of that order, that was the speed. Now, what speed we got for the switch? So, we have something like, let us say we want 50 gigabits, which will be 50 by 8 is 6 gigabytes and RAM is 200. So, RAM is definitely faster by factor 40 or so, right. Okay. Yeah. So, RAM is definitely faster and the cache is even faster. So, you can see that switch, you should not, you avoid a switch if possible. You can do your work in a single node, that is best. Do not go to 2 nodes if you can avoid it. That is why in modern machines you put more and more GPUs in a single node and put more RAM. So, you can do your work within a single node, great. Okay, now connecting the nodes. So, we have now HPC. So, our supercomputer is connected by fat tree. So, these are racks and this is called leaf switches. Okay, level 1 is leaf switch and spine switch. So, in a tree node there is a spine and then there are leaves here. Okay. You can, yeah, I mean, okay, maybe not so important, but this is a nice thing to learn. So, this is a fat tree topology with k equal to 4. Okay. What does it mean? Each switch has 4 ports. Okay. So, this is a fat tree structure and that means this link will be fast link. Okay. Here we have 4, this is a switch, no? It has 4 connections, yes, 2 here and 2 here. Every switch has 4 connections, you can check, and all 4 are connected, they are not lying waste. Okay. So, I connect 2 PCs to the switch or 2 nodes to a switch, not PC, 2 nodes to a switch, and then there are 2 connections going out. Here also 2 connections going out. So, if I want to go from this node to that node, I can go via this, go that way and come here. Okay, this is a long route, but we can reach anywhere to anywhere, but this is a redundancy. This is one connection, I can go from here, I can go here and then here. So, there are 2 paths. Okay. So, you should have redundancy, because it is possible that I want to talk like this, but maybe this process is talking to this via that same channel. So, the system is wise enough to say that, okay, you go like that. For the you have redundant roads, you have more roads. So, you can follow a road which is less busy. Okay. So, these are basically more and more roads are here. Now, k equal to 6 switch is more crowded. Okay. So, there are 6 connection per switch, okay, 6 connection per switch. Well, you can see that there are 6 in each of them. Okay. Now, let us quickly look at one more architecture. This crossbar I discussed. Now, crossbar has many links, but within a node or for simple connections, this is called Omega's connection. This is called Omega connection. So, it has less wires this one, but you can reach anywhere to anywhere in more than one hop. This requires only one hop, anywhere to anywhere one hop. Here I want to let us say go from 0 to 6, then what will I do? So, I have to retrace back here, I need go there, and from this side I need to go there. So, I need to use this branch and come here. So, 1, 2 and 3, I do 3 hops and I can reach 6, but it is more expensive, I mean in terms of time, but I have less connections, which is better for engineers who connect, or cheaper for the switch. So, omega connection is also used for networking nodes. Now, this is the last point, this is called RDMA. So, typically the data I want to go from one node or to another node, this is application, this is your program, C program, and this is a C program. I want to go from I mean basically this is my RAM. So, if I want to take the data, some data from here to there, what will I do? I make a copy, okay, there are copies being made, the MPI, that is a problem. So, you will make a copy in sockets. Okay. So, in RAM you need to have enough space for this buffer, and then this is put in TCP call, this is called TCP, transport protocol layer, I think C for something, transport protocol, and then it goes to the this data, this purple data will go to NIC and it will send here, then it goes to this new processor, and there I make another 2 copies. So, how many copies did I make? 4 copies I made, very expensive. If you use data, then copying is expensive, and that brings down your performance. So, with this new architecture RDMA, we make a, we straight away send the data to RDMA device, that I go to the new node. So, there is no copying, data writes, data is sent from RAM and put in RAM directly. Okay, so, I finished on time.